about, understanding how to manipulate these nodes. So we found that the problem was approached by other people before. A guy, that's another name, was Middleton. So this guy modeled the same process, similar, okay, and by using this specific model. This model is called a mixture. Now, what is a mixture? A mixture is a very clever way to represent a non-Gaussian distribution by a sum of Gaussians. So, having a sum of Gaussians is very attractive because, it's in a very simple way, you can describe a non-Gaussian by sum of Gaussians. Now, so let me spend, just a word because, later on in the course, we will spend a lot of words about the non-Gaussians. Okay? So, so what Middleton did is the following. So he said, if you have a non-Gaussian random process, you can describe these non-Gaussians as sum of Gaussians. Now, let's assume that what is the probability is theta. Okay, so let's assume that my theta, so my p theta, see, yes, my p theta is non-Gaussian. So let's make the assumption that my p theta is this one, okay? That's theta. Now, so how can I describe these clearly non-Gaussian distribution? So, Middleton and others say the following. These non-Gaussian can be described by a sum of Gaussians. Okay? So that means that this p theta can be described as a sum of, we call this one as theta hat 1, this one as p theta hat 2, and this one is theta hat 3. So these p theta can be approximated, but this approximation becomes an equality, as Gaussian on theta that has the mean in theta 1, okay? And there's a standard deviation over a variance sigma squared 1, where sigma squared 1 is the standard deviation of the Gaussian, okay? Plus is another Gaussian, okay, with the mean theta 2 and the standard deviation of theta 2, plus the third. So it's a sum of Gaussians. Now, these are sum of Gaussians. Since the integral of each of the Gaussian is 1, so if I sum the 3 Gaussians, the integral will be 3. Okay? Because I'm summing, these 3 functions that have the integral equal 1. So in order to compensate, to cope with that, I introduce a parameter which is P1, P2, P3. Now this P1, P2, P3 is made in such a way that the P1 plus P2 plus P3 is equal 1. Okay? So in this way, I can model a non-Gaussian as a sum of Gaussians. Okay? This is a sum of Gaussians. Okay? Now, this is the model for this. It's called Gaussian mixture, which means it's a mixing of Gaussians. Okay. Now, what I'm indicating is for a one-dimensional variable is general for any multidimensional variable. Okay. So in general. Now, this sentence for general will be useful at the end of the course, okay? this general says that, you know, this p theta is equal to the sum on the pk, and then is a sum of Gaussians, okay, where the mean is mu k, and the variance is replaced by the covariance ck. Okay? And then, you know, it's a summing for a set of Gaussians. That's the most general one. Now we will see that this general formulation is important for learning method that has to do for classification and clustering, okay? Or also known as a k-mean or expectation maximization methods. Okay, so it's a basis for that. And this representation of Gaussians is useful for other setting where, you know, we need to find an optimum classifier. Okay, so now let's see the application in this case. By the way, let me put another comment. In case you need to simulate a Gaussian mixture. Okay, you can simulate in the following way. Very simple. So you can make, let's go here with that one. Okay. Okay. So if you need to simulate that, you need to put, you know, 3 generator. Each of the generator is generating, you know, a normal with a theta 1 and sigma 1. The second one is normal with a theta 2 and sigma 2. Normal with theta 3 and sigma 3. So you have 3 generators, which are generating 3 Gaussian variables. And then you put a switch, which is getting theta, and this switch is randomly chosen with the probability P1, this one, the probability P2, the second, with the probability P3, the third one. Okay? In this way, you generate a Gaussian mixture because it's combining 3 different Gaussians. So by choosing the different probability, you can select, you know, the 3 normal distribution. In MATLAB is 4 lines. You will see that in the book. Okay. So now going back to the point. So I made a detour on the Gaussian mixture. Okay. So let me go back. So if I go back here, okay, the Middleton, okay, they started to describe that theta. Remember, theta is the so-called noise. Okay. So now theta is modeled as alpha or beta, where alpha is a certain Gaussian variable with a mean mu alpha and you know, with variance sigma alpha squared, and beta is mu beta and sigma beta squared. Now alpha is modeled with probability p, and sigma and beta is modeled with probability 1 minus 2. Now for the specific setting of Middleton, he said that the mean is 0. Okay. Now, you know, what is alpha, what is beta? Now, alpha, in the case of Middleton, alpha, you know, is representing, I think it was alpha or beta that is spike. I didn't say. Okay, I didn't say. Anyway, so you can, you know, make it this way. You can model, okay, with alpha, the spike. So what is a spike? A spike is a big amplitude. So, you know, if a spike is modeled by alpha, that means that the sigma square alpha is much, much bigger than sigma square beta. So I'm modeling a distribution represented by a big spike with probability much smaller than 1. So a big spike that happens with a very low probability, then superimposed to another random process, which is represented by sigma beta that is very, very small. Okay. And that's why I'm mixing the two probability. Now, So, the probability of x, which is calculating, so is defining the metric to compute the MMSE estimator, is simply the compound of a Gaussian noise. Remember, Gaussian is a variance that is sigma w, so that is normal with zero mean and sigma squared w. Okay? And so the probability is p times the probability when there is alpha and noise. So the two phenomena are, how can I write here? So the two phenomena are with the probability p and 1 minus p. So with the probability p, I have x is equal to theta alpha plus w. But with the probability 1 minus p, I have x equal beta plus w. Now, so let's plug this one inside. So with the probability p, I have x, so I have x is equal to alpha plus beta. But since alpha is Gaussian, beta is Gaussian, alpha is zero mean, beta is zero mean, then I just take the variance, that is the variance of alpha plus variance of beta. So the variance is sum. With the probability 1 minus p holds this model, and this model has the variance that's sum, as in the previous case. Now, what is the MMSE estimator? Now I go back to my magic formula, and the MMSE estimator is by taking the derivative of the PDF and divide by the PDF itself, or if you like the other way, take a logarithmic and then calculate the derivative. So I can make it in the closed form. So I go there, now that I have it. So I calculate, now to get the estimator, I need to calculate the logarithmic, and then I calculate the derivative with respect to x, okay, of that one. So I have a Gaussian, so the logarithmic of Gaussian. The logarithmic of Gaussian, since the Gaussian is exponential, x to the minus x squared divided by the variance. When I take the logarithmic, okay, so that part, the exponential goes away. Now, and you compute the derivative for that. So, manipulating, it comes out of this strange formula. Now, let's plot it. If I plot this strange formula, it comes out that my estimator has this strange behavior. Now, but this strange behavior is very intuitive. This strange behavior is illustrating the following. So, sigma alpha is 10 or 50, sigma beta is 0.1, very small, and then sigma w is, I think it should be 1. I think I remember it should be 1. Okay, so sigma squared w is equal to 1. So, if a sigma alpha, as you see here, if sigma alpha is a 10 or 50, 50 means very big spike. So it's a 50 times much bigger. Now, how is the behavior? You need to read the estimator this way. Every time I have an x value, I go here and I output the corresponding value. Okay? So that's the behavior. Now, let's look at the dashed line. This dashed line means that the estimator is not only linear, but does nothing. Because every input goes as output. So, if this happens when the probability is equal to 10 to the minus 5, but this probability is the probability of a spike. So having 10 to the minus 5 means that the probability that having a spike is very, very small. So if the probability having a spike is very, very small, means that every value that I have, I output that value. If the probability of a spike is 10 to the minus 1, let's consider this other case, this other extreme case. So if the probability having a spike is 10 to the minus 1 here, what does the estimator? The estimator does the following. If the amplitude is very small, almost do nothing. If the amplitude is too big, set to 0. If the amplitude is halfway, then smoothly put to 0. Now, even if this behavior seems very strange, but it's reflecting a kind of common rule which is commonly employed in manipulating data when affected by spikes. The manipulating rule is commonly said as the plus minus 3 times standard deviation cutting. What does it mean? It means that, I take my data. These are my data. I take my data. I compute the variance of the data, which means the computing power. Okay. Then I establish a kind of window which is 3 times standard deviation around. Okay, with respect to the value. Now, if the value is bigger than plus minus 3 standard deviation, I take the spike value and I move to 0. Okay? So, in this way, every spike is reduced and put to 0. Now, this is most obvious. Now, how this rule is reflecting into our experiment. It says in this way. Now, when the standard, when the data is bigger than plus minus 3 standard deviation, my estimator is preserving the data. When the error is bigger than 3 times standard deviation, I set to 0. Now the orange one is the one that is plus minus 3 standard deviation. The green one is the smoothed one, which is obtained by the MMSE estimator. So the MMSE estimator does what the intuition is suggesting us, smoothing the data when they are too big, keeping when they are down. So applying the MMSE estimate and comparing to the true data, now I don't remember which one is the true, but so you can see that they are following one another. Okay? And the big spikes which corresponds to these values are cutting out. Except probably this one that has been reduced. No, it's here. Okay? So that's another tool that I'm offering you to manipulate the data such that you can use, reuse the data and remove the possible spikes in the data. If you remember, we discussed about the robust estimation. Robust estimation, you have the data, and from the data you remove the outlier. You try to remove the outlier from the data. Now, otherwise you can use the MMSE estimation, and in a smoothed way you remove the outlier. Or you can use it plus minus 3 times standard deviation, which is similar to the to the MMSE estimation, which is more sharp. Which means, if you are bigger than 3 times standard deviation, which means if you are 3.1, you put to 0. The smoother one, which is an MMC, is a smoother and is smoothly putting to 0 the values. Now, as I started, when I started the course, I say I'm not giving you the solution, I give you the tools. So you have your box, in your box you have a set of tools. You need to decide, you need to take the responsibility to decide which tool is better for the problem you need to solve. Okay, this is part of Friday. Tomorrow we have the exercise, right? Let me see. Okay, these are some special settings. Okay, now I give you that. Please study this. Okay, study that, because I mean it's kind of obvious, but you give you the slides so you can study that. It's also in the book. Now, I want to spend a few minutes I'm closed today, so I want to spend a few minutes for tomorrow to let you think about. So, as I told you, the exercise tomorrow will be the homework of last year. Okay, so the homework number 2. Okay. So, as you see, we are growing in complexity, okay? And you are growing, even you are growing, okay? So I hope you feel yourself, you get stronger day by day, okay? But you are spending your effort, you are spending your time. That's why it's not me, it's you that you are spending your time, you get stronger and stronger. Now, so you will read the text, but let me give you some insight. Tomorrow we start at 2:30, so you all receive the email. We probably spend the first few minutes to discuss a little bit. Okay, I expect that everybody of you downloads the file before tomorrow. Okay, so you can download the file. In case you have a friend that has already done the homework number 2, you're better that I don't discover that you are just faking the exercise of tomorrow. Okay, because it's an exercise for you. So it's not to prove that you can do it. It's that you need to work on that and gain the solution by yourself. It's like you need to piece by piece to understand that. That's the only way you can grow. Okay? So nobody, is growing by just copying the solution from others. Now let's read together, because that's what I wanted to do. Now, interference mitigation or reduction is crucial in many applications, statistical signal processing. Okay. Audio and music live signal offer an excellent setup to each other, to each one individual. Evaluate the effectiveness of a specific signal processing method. So that means that you enjoy. Okay. One stereo signal. Now, so you have a one stereo signal. S1 and 2 is left and right, whatever. It's affected by noise, which is W. The noise is coming by a filter. Now, my suggestion, sketch it. Sketch, okay? So, we have our S signal, okay? ST is a signal, and that is affected by the noise W. So, the noise is coming from another end. So that means that I have a noise here. The noise is stereo, okay? So it's a 2-channel noise. So now what I do is that one. So this noise, this signal, okay, how did I call it? SN. Okay, so this is the true signal. Is a filter by a filter H. Now let me use the notation by my friend colleague. So to indicate these 2 channels indicates with 2 arrows. Huh? So that one by filter with H, that one is superimposed with that. This is what we measure. That is S in. Okay. This S is affected by noise. Clear, okay? So then I don't give you S, I give you S in. So this is what you have. That's the data. So when you listen that, it's affected by a different kind of noise. Now, you will see that, the noise is impaired by channel H. This channel H might be time variable. Okay? So because of whatever reason. If you think it's a headset, and then you are moving. And since you are moving, you get a different noise. Now what I do is that I take a reference, and the reference is by taking n noise, which is never measured, having the filter GK, GT, GK, GT, and this one sets as reference. Okay? Now what I need to do, I do this. I don't give you filter, I don't give you G. Okay? So what you have to do is essentially to take these as SR, SRF, filter by a filter that you don't know. Okay? After filtering, you need to remove with respect to SN. And this is the error. But you know, since the error that I measure here, and since SR, SRF is depending on the noise, so what is the residual error that you can listen here? This error is SN minus the noise that has been filtered. So the filtering that I can get here is approximately H times G to the minus 1. Because what I need to do is to deconvolve G and convolve H. So by doing that, this error is approximately equal to ST, stereo, which is the music. So after that, we get a clean music. Okay. Now, but since this filter here is time varying because it's adapted, then what you need to do, you need to compute the adaptation loop. And so the adaptation loop, your tools that you have in your box are that you have LMS filter, you have the optimum filter, the LMS, the RLS. Okay. Now the optimum filter is for stationary. So if the optimum doesn't work, you need to go to an adaptation rule. If you use the RLS, if lambda is equal 1, so you use a damping factor that is equal 1, that means that you have no memory. So with lambda equal 1 is equal to the stationary one. So my suggestion is check a lambda, because probably you need to implement a filter that has a lambda that is not equal 1. Last comment. Remember that the filters are 4. So every time I write this or that, which is H or G, this is left, right, left, right. So you have one filter, one filter, one filter, one filter. Remember that every time I write this G, you have 4 filters. Okay? So I don't know, you have a filter G11, G12, G21, G22. Okay. Then that's all you need to remember. So you need to remember that you have a 4 filters. Now, if doing the workshop in the previous time with Matera, if doing the homework of number 1, you learn how to write a convolution matrix, okay? In case there are 4 filters, you need to write a convolution matrix that is block partition for the 4 filters. Okay? So that means that you need to generalize what you learn to the case of 2 by 2. And when I say 2 by 2, it means that the convolution matrix are, 4. 1, 2, 3, 4, right? Okay? Remember that. So you have 4 filters, 4 filters. This guy is 4 filters. Okay? Now, these so download the signals. These were from what I saw from your colleague that did the homework last year. The major difficulty doing this homework was to write the 4 filters in such a way that the word 4 filter works. Remember, last comment, remember that the filters are causal, anti-causal. They might contain positive component or negative. Okay? The filter, when I say filter is 20 samples, it might be 10 samples positive, 10 samples negative, 21. Okay? Remember that. Okay. That's all, you know, so we meet tomorrow and come with all the best patience and, you know, remember the cables, connectors, everything, headset, and we will enjoy. You will enjoy because I sit there and do nothing.